Okay, hello. We are going to be utilizing power series to write, I guess I need to turn off the television, to write this function as a power series. So, there's a slightly different process for this. We can always use Taylor series and Maclaurin series for these examples, but computer timed out. But there's actually a simpler way of doing this because our textbook actually goes through the process of finding Taylor series for specific functions. One of those specific functions is cosine of x. So they went through the same exact process that we did for the 8 divided by x video. Same thing, using a Taylor series, going at a couple derivatives, noticing a pattern, plugging all that in, and then finding the simplified series, I guess, is the best way that you can describe all of those steps. So here, they actually already did that, so it kind of saves us a little bit of work. Here, if we just have cosine of x, in your textbook, it says specifically that this equals the sum as n equals 0 to infinity of -1 to the n, so this is an alternating series, x to the 2n divided by 2n factorial. All right. So what we can do, since we already have a piece of this, all we need to do is actually just subtract 1 and then divide by x for all of these things. So we're just basically modifying this. So it looks a little freakier than what it actually ends up turning out to be. So the best way to do this is to write out these actual terms. So we'll plug in 0 for all of these. Anything to the 0 is 1. So this would be 1 times 1. 0 factorial is 1. So this actually ends up being 1. And then if we continue this, we actually end up getting all of these terms, x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, so on and so forth, alternating series. So we are just going to modify this. We're going to look at these specific terms and see what we can do to have it representing this function rather than just this function. So all we actually need to do, first step, is just subtract 1. This isn't too bad because we just have a 1 here floating out in the abyss, basically. So we're just going to subtract 1 from that. So we have cosine of x minus 1 equals all of this, not including our 1, because that is the part that we're subtracting. So we are just going to say x to the 2 over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial. Continuing on and on and on forever. All right, then all we need to do is divide by x. This will be for each term. This wasn't for each term because this was just simply subtracting 1 from our total. We had a 1, so we just need to subtract it. But now whenever we divide things, we need to divide by each term. So we are just going to divide each term by x. We're going to say negative x squared over 2 factorial x plus 4 to the 4th over 4 factorial x minus 6 x to the 6th over 6 factorial x. That goes on and on forever. So we can actually do some simplification here. This x squared is going to cancel out with this x. This x to the 4th is going to reduce to 3. This x to the 6th is going to reduce to the 5th, and so on and so forth. So all we need to do is now rewrite this. I'll rewrite it over here so it's a little less messy. Negative x to the 1 now over 2 factorial plus x cubed over 4 factorial minus x to the 5th over 6 factorial, so on and so forth. So now I'm just going to utilize this function so that I can rewrite this in series form rather than all written out like that. So since by subtracting 1, we got this term because when we plugged in 0 for n, we got this to the 0, this to the 0, and 0 factorial. All of those things equal 1. So the way for us to just subtract 1 is just start at n equals 1 rather than at n equals 0, and that is the part that takes away this first term. So that is going to be n equals 1. All right, and then now we look at our exponents. Previously, we had x to the 2n. So now we are just going to have x to the 2n minus 1 because we already got rid of our first term, so we technically don't really need to worry about subtracting anything else. So we just are going to start with our second term. Our second term had n equals 1 in there, so this would be to the 2, to the 4, to the 6, because it's 1 times 2 is 2, 2 times 2 is 4, so on and so forth. So I just need to reduce by 1. I need to go from 2 times 1 minus 1 to get to 1, or 2 times 2, which is 4, minus 1 to get to 3, so on and so forth. So before I get there, I still need to have my x to the negative 1 in there to the n, because my signs aren't changing. This is n to the 1. Negative 1 is going to be my first term, so I still am not going to change anything there. It's still going to be negative 1 to the n, and then this will be x to the 2n now minus 1, because that is when we divided our x. All right, and then our factorials did not change as well, so that part of this problem is not going to change. 2n factorial, because that was not impacted. So this is going to be our series for this guy. All right, and now we need to do a second part of this problem. So I'm going to write my series n equals 1 to infinity x to the 2n minus 1 over 2n factorial. All right, and now I'm going to erase everything, right? It's everything that I have that I need, because we need to now integrate, because that is just the problem that they're asking us to do. Erase. This thing has not been erasing too nicely for me today. Okay. All right, so now we just need to integrate. All right, so I'm going to integrate my sum, n equals 1 to infinity, negative 1 to the n, x to the 2n minus 1 over 2n factorial. So here it definitely helps to understand what part of this is a constant, because again, we can pull out constants whenever we are integrating. So that is going to make our life a little bit easier. So what I can pull out, since n is just going to increase and turn into a number, this will be negative 1 to such power. This will be a factorial, however big. But that is not the derivative, or the integral that we are taking respect to. So the only piece that I actually need to take respect to is this piece here. So I can remove my negative 1 to the n, and then my 2n factorial, and push that on the outside of my integral. And then I just have x to the 2n minus 1, derivative of this, integral of this, So integral, all I'm going to do is add 1 and then divide by whatever my new exponent is, because this is our very simple power rule. So by adding 1, I basically just get rid of this, and I'm just going to then divide by 2n here. Not too bad. So I'm going to say negative 1 to the n over 2n factorial. And this is going to be x to the 2n divided by 2n. All right, plus c. Sound good? So, I guess we could smush these together. What format does she need? I'm curious what actual format this will take. I would just kind of maybe smush these together and say -1 to the n, x to the 2n over 2n times 2n factorial. I believe we can't smush that in there and make it 4n squared because that would end up increasing our factorial pretty aggressively. That I'm not 100% sure on if there's any simplifying that we can do to that respect, but I believe that this is going to be all that we can do for now. I'm trying to think, because if we plugged in, let's say 2, that would be 4 times 3 times 2. Four times 3 times 2, so that's 24 times 4. 96. And then if we did 4n squared factorial, there's no way. 2, 4 times 4. Factorial. There's no way 16 factorial equals 96. Yeah, there's no way. That's a huge number. Yeah, so it's going to have to stay on the outside for now. So yeah, so there we go. And since these videos are getting very large very quickly, and I'm already having to upload these on YouTube, I guess I'll start uploading this one, and then I'll go for the utilizing series to evaluate a limit in the next video.